Okay, welcome everybody. How's it going? Good? Yeah, a different room just for today. What do you all think? A little bit tight, right? A little bit tight. Well, how's it going? So, we're very grateful to Kate for allowing us to be here and use this space while our space that we normally are in is being utilized for a very nice event for the School of Engineering. Okay. Administratively, any questions about what's going on? Yes?
I'm just curious, what's going on here?
Okay, so there is something called the Medal of Excellence banquet or dinner. I'm not quite sure what it is. And so it's an opportunity for alumni to come back and participate. So once you graduate, if you want to participate in the dinner, you can buy a ticket and you can go. And then a few people are recognized for their contributions to the School of Engineering. Okay? Yes?
Can you turn off the mic, Paul?
Let's see. Does the microphone...
Oh, yeah.
Okay, is that, whoa, is that better? Okay, all right, thanks. And of course, your cooperation, whoa. Okay, your cooperation is appreciated in, wow, hello, folks. It would be great, just for now, I like the conversation because we need that when we do the problem solving. If I could get your attention, hey guys. Folks, thank you. People are trying to listen, all right? So it's great to be here. Today, any other questions administratively before we get going? Okay, just note, please take a look at the video. There's pretty much one that explains how to do the lab, okay, on the tab for lab, Tensile Testing Lab, before you go to the lab, all right? I think those who did the lab on Tuesday did an excellent job. There were some hiccups, and I had a chance to kind of do a debrief with the TA and the lab assistant, well, mostly the TA. In some cases, one group was getting the wrong answer when they thought they were getting the right answer, and the group that thought they were getting the wrong answer was actually getting probably the right answer, okay? But that's just for one problem. And then so there was a question of whether there's an issue with calibration. It looks like the machines are doing just fine. But we are still getting calibrated ourselves in terms of how to best run the labs. So today is day 2 of the labs, and I hope it goes really well for those of you who will be watching this after you're done with your lab, okay? And for those of you who did the lab, thank you. One team finished very quickly with about 10 minutes to spare. One team decided to call it at the time. I can respect that for the first time. And one team stayed after for like 30 minutes, all right? Really, it should be possible to get it done in an hour and 20 minutes. At least that's our goal, okay? But we'll see how it goes. Any questions on that? Okay, everyone know when the exam 1 is. What's the date for exam 1? 10/10, October 10th, right. That'll be 2, yes. How many questions? I don't know yet. It's not written. Huh? I mean, so there's been this question of what's the exam gonna look like, right? And that's when the room goes quiet, right? No, so take a look. We've got examples from this year, right? From the spring and from the summer. Those I would take a look at first. Okay, those are probably the closest. Then you've got fall of 2022, and then you've got some older ones. The older ones, I think we're a little less friendly, okay? But the more recent ones should be more indicative of what to expect. So both the format, I mean, I can essentially guarantee that the instructions at the top of the exam are going to be identical to what you saw on the earlier exams from this year. Okay? Any advice from those who took the lab, did the lab this last Tuesday, for those who will be doing it? Yes.
Watch the video beforehand.
Watch the video beforehand. Okay, any other advice? Yes.
Where's the video?
Okay, so the video is... So underneath all the sessions, okay, there's a new one called Lab Information. And then there's a video, and you can be so happy because you don't have to see my face at all. You just see my hands. That's all you see. My hands over here, and then you see the screen over here, okay? And I think that will greatly facilitate. I don't know, it's fun in some respects. You get to tighten screws, you get to loosen screws, you get to grip something, you get to turn a crank, right? I don't know, it's fun. I thought it was fun, all right? Anything else? All right, so what I want to do today is go through a numerical process. That's a fancy way of saying a simulation, all right, for how to predict the stress and strain in an axially loaded bar, okay? And you're like, oh boy, this is so repetitive. We've done this axial bar business a bunch. True, okay? How many of you, though, have simulated forces or stresses on structures in a finite element analysis package? Yes? What were you doing?
SolidWorks.
SolidWorks? Yeah. Okay, SolidWorks, great. What were you simulating?
I was doing topological optimization to decrease the weight of a frame.
Okay, awesome. Was this for a particular vehicle of some sort that has 4 wheels?
No, it was for a mouse.
Oh, so the computer mouse?
Yeah,
Okay, cool. Was this
just for fun.
for fun? All right, great. Okay, so yes, one thing that you can do. Okay, anyone else? That was really awesomely detailed. So, what you were? What's your name? I'm sorry.
Frank?
Okay, so I'm guessing what you were doing, Frank, right, is you were creating a CAD model, and you were using parameters to describe the dimensions, right, of this computer mouse, right, and then those dimensions you could change, right, but you still have the same geometry, and you had some limits for what those dimensions could be, or no? Were you changing the shape or changing the dimensions when you're doing topological optimization?
The shape was there. It would just cut away material that was not needed.
Okay, all right. So it was more of a topological problem. Okay, so you're starting with an object, right? And then what are you trying to do? You're trying to figure out where the maximum stress probably was, right? Because the maximum stress is going to be where the object fails, right? So what happens when you take away material?
The stress goes up.
Yeah, right. I mean, if I've got if I want the world's strongest mouse, computer mouse, right? I'd probably just take a hunk of steel and put it on my desk, right? But that's not very useful for carrying it around for other reasons or cost, right? So this is a big deal with the aerospace industry. It's also a big deal, right, with products that mechanical engineers or industrial designers might be creating. Good. Okay. And so what happens, right, is the computer program, if it was doing some type of topological optimization, were you controlling what you were cutting, or was the computer using an algorithm?
The computer was using an algorithm.
Okay, so the computer is using an algorithm, which means that it would take away something, right, and then it would look at the stress, okay, and then say, oh, it's above or below, and you probably had a safety factor. So you're if the yield strength of the plastic is, 150 megapascals or something like that, right? Maybe put a factor of 1.5, whatever it is, right? And you want to make sure that you're below that for the standard cases of loading, right? So you probably have okay, this is what we expect either from a drop or from someone using it, okay? And then pre-calculating. So when you do this optimization and simulation, all right, yes, you go through a circle, right? And this is machine learning, right? That's really big deal right now. Okay, So with machine learning, you need data, right? And so sometimes that data comes from actual physical experiments, but other times the data comes from simulators, all right? Physics simulators, like your computer games, right? There's a bunch of physics simulation going on behind the scenes. So it can run a bunch of scenarios, right, to teach itself, okay, how to essentially get the optimal outcome or how to predict what's going to happen next. All right. So that was maybe long-winded, and I'm glad. Anyone else use finite element analysis? Okay. So we're not going to use SOLIDWORKS today. All right. We're going to use open source. The open source community has come a long ways, and so you should be able. If you have a PC, you should be able to follow along here. If you don't have a PC, you can use the computer lab and you can use the PC. Unfortunately, the software, one of the pieces of software that we're using, only runs on a PC. Okay? So let's go ahead here. Imagine okay, you have a crummy looking bar like this. Okay. All right, and it has some length. All right, and it has some cross-sectional area. Okay, and the material inside it has an elastic modulus and has a Poisson ratio. Okay. If I want to know how much it deflects, you guys tell me, what's the equation at this point? We've done this a few times. What is going to be the deformation, the axial deformation of this bar? Huh? Flee. Okay, good. All right, so delta equals FLEA. No. It was a joke. Not a very well received. Okay? So it's FL over EA. All right? And what is the stress in the normal stress? Okay? So like if I'm thinking about stresses, in this direction, what is the stress? Yes. Yeah, F over A, right? Okay. And what is the strain? And I'm going to call this sigma x. Whoops, not sigma, sigma x. I'm going to call this epsilon x. I'm going to call this the x direction, y direction, z direction. All right, so what is epsilon x? Yes? What's that? E divided what? I'm sorry, say that again? Well, that would suggest it's a constant, right? If you gave me E divided by 3, that would be, it just means it's a constant. I'm asking for the strain. The strain is going to be dependent on how much force, right, is being applied. So the strain, right, is the change in the length over the initial length, right? Okay. So one way to look at it is going to be, you could look at it this way. Okay. All right, that would be one way to look at it. Okay, another way would be, if I know the stress, right, I know that sigma equals, if this is a linearly elastic behaving material, okay, then it's a sigma is equal to E epsilon. All right, so then this is going to be the sigma x over E, right? And so this is going to be F over EA. Okay? Any questions on this? So you're like, why in the world would I want to simulate this? I know it all. True. Okay? Why do we do simulations? Because we want to be able to do more complex. We want to be able to understand what's happening in more complex geometries. But the baby steps in simulation, all right? One day, maybe you'll look back and you'll be like, okay, I remember I was told this. Okay? Sometimes this happens, it happens so often. It happens with me personally, happens with a lot of people. You want to you have this complex problem, and what you want to do is you want to just simulate the living daylights out of this complex problem. But that's not the approach that's going to necessarily lead to the fastest determination of getting what you want. So the first thing you should do is find a simple problem. Okay, oops, that has an analytical solution. Okay, and I'm sorry, this is hard to write on. I know my handwriting is bad, but it's even worse right there. Okay, why is that? So this is what we just did. We just found, we know what the answer should be, okay, by basic mechanics, shall we say, right? Then we simulate that problem. Then we confirm the output of simulation is accurate. And then we go on our merry way of building more complex simulations. Okay? So if you skip the first 3 steps, you have no idea if your simulation is even behaving correctly. Okay? And it's often a good idea to start with baby steps. All right? Baby steps. With simulations, garbage in, garbage out. Okay? You can make really pretty pictures that have no relevance or that do not have quantitative or even qualitative properties that are accurate. Okay, so if you look in your notes, okay, for the online notes, we can find a problem that's given. So this is one iteration of session 8, Q1. All right, and it says, actually, maybe I'll just do it like this. It's better. Okay. Says we have an axial load bar that has a length of 11 centimeters. All right, so L is 11 centimeters, a width of 1 centimeter, and a height of 1 centimeter. So that means area, cross-sectional area, is going to be 0.01 meters times 0.01 meters. Okay, so that gives us 10 to the minus 4 meters squared. Says it has an elastic modulus of 176 gigapascals. Okay, and a Poisson's ratio of 0.3. And it also says that we have an axial load of 1,838 newtons. Okay? Did I forget anything? It's saying we want the axial strain along the length of the bar in microstrain. Okay? So, what you can do is first build the model, the geometry, okay, and then run finite element. Now, SolidWorks and other commercial packages are nice because they let you do both right there and then. In some companies, what happens though is you have one group that focuses on design and you have another group that focuses on analytical simulation. Okay? And the designers, they do their thing, and then the simulators, they do their thing, and then it goes back and forth like this. This is not the most efficient way to do things, but it is actually a very careful way to do things because multiple people looking at different problems or different aspects of the same problem. Okay, so if you like, you can go ahead and use FreeCAD. You could use SolidWorks, you could use something else, okay, but FreeCAD is readily available, and this package will run on Windows and Mac, all right? And I don't think there's a much simpler way to put in this geometry and get an STL file, right? STL is a file that describes the 3D geometry. So what you do here, and so from here you probably want to pay a little bit of attention, and it's going to be recorded, and there are already other videos that explain how to do this. So you don't have to like take copious notes, but just pay attention that we're starting. So we create new, I click there, and then this comes up, and you have this unnamed thing. Over here, we're not going to go to part design, which is what you normally use for extruding and other things. Since this is an extremely simple geometry, we're going to use the part setting. And then we're going to use a cube, bring in a cube just like that. And we're going to go ahead and we're going to change, we're going to edit, whoops, see I can't even do things. We're going to edit the geometry. What did we say? We have a length of 11 centimeters. And we have a width of 1, we'll just do it, we can even be dumb here. We'll just put 1 centimeter by 1 centimeter. It's that nice, okay? And it converted it for us, all right? So you see, now we've got our bar. Very simple. We can export this, all right, to the STL format. So you're going to come down over here, make sure, I don't think STL is the default the first time you use FreeCAD, but maybe it is. But you're going to export it to this STL mesh, okay? And I already have one there, but we can do the unnamed cube, all right? It's going to go in that spot. Okay, so we're done here. You can save this in its native format if you want as well. So you can save it as this FC FreeCAD, I guess STD, whatever that is. All right, but we're done. So I'm going to close this. I'm just going to discard it. Okay. Now, Prepo Max is an open source piece of software. All right, which uses an open source physics or finite element engine, all right, called Calculix. All right, so what you do is you go to downloads, and you can see that they're pretty active. The latest one came out just over a week ago, all right? So you download this, and I understand some people, haven't used computers that much, or how do you say that? They don't use zip files, like, whatever. So I kid you not, like, it's been rewarding just to walk around and be like, okay, this is how you extract a file, all right? So we'll go ahead and we'll save this zip file, all right? And it is going to actually go right to my downloads. And it's taking a little bit longer. When I was a college student, that would have probably taken like 10 minutes to download 67 megabytes, all right? Okay, so now it comes up and we right click, okay? And we're going to extract all. So you hit extract all and you can choose where it goes. I'm just gonna do the desktop, maybe. Well, let's just do it, maybe not, let's just do it right there. So now it extracts. This is not how you normally run Windows programs, right? Normally you have like an executable or an MSI, okay, file, and then you had to use the Windows installer. Once this is extracted, that's it. you don't have to do installation. You go into the folder and you just click Prepomax. And you say it's okay. Okay, run anyway. So you're trusting it. Okay. All right, and then this is what comes up. Any questions up to that point? Good, right? Okay. So what we need to do now is bring in our file. But first, we have to create like a new model here. Okay. So we're going to create this new model, and we're going to use meters, kilograms, seconds, whatever, centimeters, or Celsius, sorry, not centimeters. Okay, and we hit OK. Okay, and then once we've done that, we're going to go over to File again, and we're going to import that unnamed cube that we just had. Okay, and there it is. Now, can anyone notice anything odd about what we see here? Anything odd? It looks like a bar. What's up?
Scale,
Yeah, what's up with the scale?
66 meters.
66 meters. That is not the dimensions we put in. We put in that this bar was only 11 centimeters long. All right. So if you use SolidWorks, if you use another software, you might run into this issue as well. Once you export to the STL format, dimensions can get messed up. So what you're going to do is you're going to come over to Geometry, go to Part, and then hit Transform, and then hit Scale. And what are we going to do? We are going to scale this thing down by a factor of 1,000. Okay? In all three dimensions, in X, Y, and Z. Then we hit Apply, and it disappeared. Buenas noches, right? It's gone. So what do? We can do a zoom to fit, all right? And it reappears, and yes, the length has been scaled by a factor of 1,000 apparently. And if we turn it a little bit, okay, we can see that it's now longer than the scale bar. What is 11 centimeters? 11 centimeters is 0.11 meters, right? So that's a little bit greater than what you see here. So we're likely on the right scale. Okay, now, what do you do next? For those of you thinking about this, what would we do next here? Right now it's a block, but what are some of the things that we need to do to this block in order to do our simulation? Okay, we had to pull on it. Okay, good. So that's a good thing, Michael. Yes, we're going to pull on it. Okay, good. What else do we have to do? Yes? Yes, so we're going to pull on one end, and we're going to have one end fixed. Good. Yes, with a force. Good. Yeah, what else? What does the computer know about this block at this point? All right, we need to give it some material properties, right? We need to give it an elastic modulus. We need to give it a Poisson ratio, all right? All the simulation knows at this point is its geometry, okay? Which is a big deal, right? That's a big deal. That's why we do these things, all right? Okay, so we are going to do those things in just a minute. There are a couple other things we have to do first, all right? So one is finite element. All right, suggests that we have elements, all right, and that these elements are finite in size, right? So what we end up doing in finite element analysis is taking a large object and discretizing it into lots of small elements that make up the big geometry, right? So in the case where you have something that's curved and you have a lot of like little blocks or stuff in it, it's an approximate to the actual thing. And in this case, it will still be an approximate, all right? But the nice thing is that cubes fit inside cubes quite nicely, all right? But it's not necessarily going to be cubes. They can have different types of elements. So you're going to see some kind of interesting things happen. So what we're going to do is we're going to mesh first, okay? And this is not how all software works, but this is how this one works. We mesh, we select the part. So I clicked on it, so now the part is selected, And we come over here and we're going to specify the maximum element size. Okay? And that's actually, this is not that bad actually as a size. We're going to say that the maximum element size is going to be 2 millimeters, 0.002 millimeters. Okay? And the minimum size is actually going to be even smaller than that. All right? That kind of makes sense. So we hit OK. And then nothing happened. All right? Because all we did is we set the mesh parameters. Now we're going to create the mesh. Okay? And we give it a second. And voila. Okay? You see this? All right? So now it's been discretized into a bunch of elements. All right? Inside that block. At this point, we can start to go ahead and assign some material properties. All right. So after let's go. We're going to create a section. Okay. This section is a solid section. Sorry, and we gotta. Oh, okay. Sorry. I guess we do have to do the materials first. All right. So materials we're going to create, and this is an elastic material. Let's just call it material. Session 8, okay? It's 176 gigapascal, so that's not really steel. I don't know exactly what this is, all right? But I'm going to go ahead and select elastic and put this over here. And look, this is also neat. I can do 176 gigapascals, all right? And it puts in all the zeros, and I can put in 0.3 for the Poisson ratio. And we hit OK, all right? Now we're going to create a section. Okay, we're going to create a solid section, and that's for the whole thing. Okay, I'm going to click on it, and we hit OK. All right, so that's our solid section. Then what we can do is we're going to create a step. So this is kind of, what do we want to simulate? We're going to simulate a static loading, right? That's what this class is about. So we're going to do static step, okay, and we're going to hit OK. And then a bunch of stuff comes up over here. At this point, okay, we're going to set the boundary conditions, all right, and we're going to, for the left side, we're going to make the left side over here fixed, so it can't move, it's stuck in space, all right. With static problems, with finite element analysis, often that's what you need to do. You need to constrain all 6 degrees of freedom. All right, of something. Otherwise, this thing can move in space. All right, 6 degrees of freedom. What are the 6 degrees of freedom? Good, that's right. So usually up, down, left, right, forward, backward, and then the rotation's about all those axes. All right. So we hit OK there, and that side's constrained. Now, there are a couple ways to apply the load. All right. What is weird, if you do this, it will come out wrong. Okay, so I'll show you what to do wrong. If you hit create and you do a load and you do concentrated force and you select this side, guess what it does? And we'll just say it's, I think it was 1838. Okay, newtons. Okay, it shows it looks good right here, whoops, okay. It kind of looks good, like there's this arrow here, but it turns out that it just applied 1,838 newtons to each and every one of these red dots on the end. Not ideal, okay? Or at least, so you have a couple, even you could figure out how many dots you have and divide by that, and then, take 1838 and do that. There are 2 other ways that you can approach this problem. One is, well, actually maybe 3 different ways. One is you can apply a pressure, okay? So you figure out the area, you figure out the forces, divide by the area, and you apply that pressure, okay? And that's what the previous tutorials, or that's what my previous approach was. There's another way. You can actually create what's called a surface traction right here. This surface traction, if you do this here, and we're applying it in the one direction. I guess I should have explained that. You see, this is X, Y, Z, 1, 2, 3. All right, so if you apply it right here, okay, this surface traction, you're done. Okay, And so we can go ahead and we can simulate this, right? So if we go to analysis and we go to, run, okay? It runs it and we're done. Okay, and pretty colors. There's another way you can do this if you so desire. Okay, what's going on here? Okay, the other way to do this is we go back to the FE model and we delete this surface traction. All right, we actually create a reference point, and that reference point we're going to put at the end of the model. Okay, so you see here it's about there, and so I'm going to specify coordinates for it. It's 11 centimeters out, it's 0.05 meters up, and 0.05 meters to the side. Okay, and we hit OK. Oh, whoops, it was 0.005. Let's edit this. Like that. Okay, you see that point is now there? And that's just because I know what the coordinate is. Then we come over to constraints, and we're going to create a rigid body constraint, and it goes through the reference point. Okay, it's already selected, and we're going to click on it on that surface, and we hit OK. Now, you see this thing is like X'd here. Now we can go ahead and we can define a concentrated force, and we can specify that it be applied at reference point 1, okay? And then we can put the 1838 newtons. Okay? Just like that. And then we can go ahead and we can run the analysis. Yeah, we're going to overwrite. Okay? Good. All right. So now we've got a simulated result. How do I, yes, go ahead.
So is this what we're gonna submit like to Canvas, just like a screenshot of that?
Yeah, but not, you gotta do one or two more things before you do that. Yes, but you're gonna do this and submit the screenshot of the result. Yes, okay? And there's also a question, right? It asks, what is the strain in microstrain? What is the axial strain in units of microstrain? Okay? Well, before we even do that, we looked at this analytical model previously, right? And we said, I know what the displacement is, FL over EA, right? I know what the stress is, and I know what the strain is. Okay, I can make all these calculations. All right. So let's do the super cheaty way of calculations. All right. Let's say we want displacement, right? Displacement was FL over EA, right? So let's go ahead and let's put in 1838 newtons, that's the F, times the L, which was 11 centimeters, right? And then what was the FL over EA? And then the elastic modulus was 176 gigapascals. And the cross-sectional area, right? It's 1 centimeter by 1 centimeter. Okay, that's FL over EA. Plug it in. Okay, it tells us that the displacement is 11.5 microns.
We could have done this the whole time.
Well, this is the analytical solution. Yes. Okay.
Like instead of having to do all the conversions.
Oh,
by hand.
yeah. So, you're saying you could have done this to get away from having to do the conversions? Yeah, I think I said early on you can use Google, but you have to understand you're not going to have Google when you take the exam. All right. So now we go to here, and I want to figure out what is the overall displacement. Okay. Let's click on U1. Sorry, let's do U1. All right, and I'm going to put. You see this? You see that it's like, okay, 1.14 times 10 to the minus 5. That's the max. That's the red part. The other thing you can do is you can add a query at the end. So I'm going to add a query here, okay? And this query at that point is telling me it's 1.14 times 10 to the minus 5. 1.14 times 10 to the minus 5. What is that in microns? Huh? 11.4. And what did we calculate? 11.5. That's pretty close. Okay? All right, so that's happiness, right? What is another metric that we said that we had? We said F over A, right? That's a simple one. All right, so let's do that. So F over A, that's 1838 newtons divided by 0.0, well, I don't even have to do that. I just do 1 centimeter by 1 centimeter. Okay? And it gives it in a big number in pascals, but let's say I don't want it in pascals, right? I did this before, so we just do MPa. All right? 18.38 megapascals. 18.4 megapascals. All right? So we come over here. We need stress. So look, stress. Now, remember we talked about sigma 1,1, sigma 2,2, sigma 3,3, sigma 1,2, sigma 2,3, sigma 1,3 early on, right? That's what these are. S11, S22, S33. That's like sigma, okay? So S11, if you do it like this, right? And we look at our node right here. Okay, now it's not quite in the center, all right? And it's at the end, so maybe that's not the bestest choice. Let's pick one over here, for example. Let's do a query, okay, right up here. Look at that. So that's 1.83 or 1.84 times 10 to the 7th. What is that in megapascals? What is this in megapascals? 1.84 times 10 to the minus 7. Yes. 18.4. So we go back. 18.38. We're pretty close. Okay? Now let's go ahead and look at strain. So strain is F over EA. All right? So we go back. And this time we'll give Bing a shot. All right? So 1838 newtons divided by 176 gigapascals times 1 centimeter times 1 centimeter. Okay? And see, unfortunately, Bing is a little bit not as friendly. Oh, I also made a typo though, so 1 centimeter by 1 centimeter. I don't think that's going to change anything. Nope, it does not change anything. So now we'll go to DuckDuckGo. All right. All right, again, not so friendly. It's a little bit upset. All right. So I guess we'll go back to Google. All right. That's an annoyingly small number, right? That's why the answer is in microstrain. So how do you get this in microstrain? What do I multiply by? By 10 to the 6. So I get 104.4. All right. Now let's see what we get. Or we get that other number, right? But we're in microstrain, all right? So let's go over to this. And we're going to now go to the strain, all right? And we're going to look at E11. And we're look here. 0.001045. What do we get here? Well, if I take away the that's the same, right? 0.000104. All right. Pretty stinking close. All right. Any questions on this? Okay. So now, when you go in for your internship interviews, right? They'll be like, "Hey, have you ever done finite element analysis?" I'm like, "Yes, I did finite element analysis." "Really? You're only a sophomore?" "Yes, we did it in my mechanics and materials class." All right. Now, are you an expert in finite element analysis? No. But have you done it? Yes. All right. And it's and you're like, yeah, there's this really cool open source package that lets you do it without having to pay, like thousands of dollars a month to be able to use the software. All right. So the next part of today's session involves thermal strain. Okay? And I'll let you all get to this, but this is maybe a little bit old and new at the same time. If you take a material and you heat it up, what typically happens? It strains. Okay, could bend? Yes. So bending can happen for sure if you have a piece of material and you heat one side, okay, and the other side stays cold, you can have bending. All right? And if it's kind of a conventional material, if I'm heating on, let's say this is my pen, and I'm heating on this side, and so the top is cooler than the bottom, which way will this bend? Up, right? Why is that? Yes, I know what up means, yes. Why is it going to bend up? Yes, so what's going to want to happen, right, is this side, the bottom surface, is going to expand laterally, and it's going to become longer, right, than the top surface, and that's going to cause there to be some strain. All right. Now, that's an interesting scenario. Okay, that's a more complex scenario, and it is possible then that you put some stress into the material, okay? Because this is expanded, and the top is actually trying to pull the bottom back together. So it's maybe a little bit counterintuitive, but it's like a tug of war. All right, the top is pulling the bottom back together, which means the bottom actually ends up being in compression. Okay, and the bottom is trying to stretch the top out, and so the top actually ends up being in tension. Okay, but this is counterintuitive, so don't think about this too much, right? Because that's opposite of what we have when we bend something physically with a moment. All right. What happens if I take a bar and I heat the whole bar, or I heat my whole pen, and it's a uniform material. It's a beautifully uniform material. What's going to happen to it? Anyone? Yes. The whole thing is going to expand, right? And when do you use this principle? When are some times when you want to, like, you've been in the shop, or maybe you haven't been in the shop, like, when do you sometimes try to heat things up? Any ideas? Let's say I have a ring. Yes. So when would you try to use a torch to heat something up in the shop? Yeah, you're trying to fit something, right? Imagine, right, I've got this ring, okay, and it's like a press fit on my finger, okay, this finger, all right? And I need, I made them, I want them to stick to each other really, really well, okay? And so one way to do that is to take the torch, warm up the outer ring, all right? And then stick it over the thing I want, okay? And then it clamps down on it, all right? And it's stuck. That's a press fit, okay? So that's an example where you would want to use this principle, okay? In the moment when I've got my ring and I've heated it up uniformly, it's beautifully uniform, okay? Actually, let's make it simpler. Let's just say I had a piece of material, again, going back to this. I heat it up uniformly. What is the stress in the material at that point? It's been heated up nice and uniform. Yes, there's actually zero stress, okay? This is an interesting situation, right? All this time we've been saying for a bar, sigma equals E epsilon, sigma equals E epsilon, sigma equals E epsilon, right? And so we've kind of coupled mechanically to say, hey, if you have strain, you're going to have stress. If you have stress, you're going to have strain. When it comes to thermal loading, okay? But what happens if I have that same bar in between two walls that do not move, and I heat it up. What happens there? So I take the torch, I heat this thing up. How much strain is the material experiencing? Okay, no, that's a good response. 0, okay? Because it can't expand. So then what's happening? What's building up instead? The stress, right? Think of it as a superposition problem. I've taken a bar. If I had just one end fixed and I hit the torch, I use the torch on it, right? And it elongates this way, right? I've got strain but no stress. I then apply a force that allows me to get to the initial length. And when I get to that initial length, I now have no strain in this longitudinal direction, but I do have stress that's built up. Okay? Yes.
Is that how tempering works?
Is that how what?
Tempering works?
Okay. So, I think what you're getting to, like, if we're tempering or we're heat treating materials, okay? This phenomenon I just described will happen at essentially any temperature you like, okay? Heat treatment of materials, you have to actually change the microstructure inside, okay? So what you have to do is you have to get to a pretty high temperature, all right? And then you have some options. If you leave it at a very high temperature, okay, that's called annealing, all right? And for the steels, okay, typically what that does is you heat it up and then you let it slowly cool. That's kind of annealing. You heat it up for a while and then you let it slowly cool. Typically, that will soften the steel, all right? If you take that material up to a high temperature and then you throw it in a bucket of cold water, all right, that quickly quenches the material and actually leads to hardening, okay? And when you take mech props or material props, they'll go through all this business with you, okay? But that's kind of a separate thing from what we're talking about now. Right now, we're assuming that we're not changing the material properties themselves when we're heating them. But I like the question, and I like the question. Yes?
So I'm a little bit confused about like what you said about constraints. So like
Yeah.
you said that when you have like one end constraint, then like you'll have no stress. But then won't the material try to expand in both directions?
So, good. So, if I have, yes, it's like Pinocchio's nose, all right? Pinocchio, right, he tells a lie. It's like I'm taking a torch to his nose, right? And it just expands, okay? Yes. Is it like potentially causing a little more cantilevered motion, causing a moment on my nose or on my face, right? A reaction? Yeah, all that's happening, right? But in an idealistic model, right? It goes this way. It's nothing's pushing on it, right? If I look at the free body diagram in an axial direction, right? There's nothing pushing on the nose. So the nose is not pushing, or my face is not pushing on it, so there's no stress. But has it changed its length? Absolutamente, all right? So you have to, this is a little bit counterintuitive, all right, initially. Maybe it's super intuitive, actually, for many of you, right? But this is where we have to, like, a little bit undo a sigma equals E epsilon, right? Because they're not always proportional to each other, okay? But if I push on Pinocchio's nose, right, and I bring it back to the original state, the net strain is 0, okay? And now that I've got some stress, because I've got a force, I've got a compressive force acting over that cross-sectional area. So it's in compression, okay? And if, so you have things where, like, okay, if I do thermal strain and I pull, right, actually that does nothing to the stress. Whatever I'm pulling with is the stress, okay? But if I'm compressing, it's a different story. All right. Well, actually, whatever that force is, that's the compressive stress. Actually, that's how it works. Okay, any other questions? So what you have the opportunity to do, okay, well, let's talk about things. strain, all right, so for the free bar, okay, with free ends, the strain can be given by the linear coefficient of expansion, called alpha, or and right now we'll call it alpha L. If you see alpha in this class, assume that we're talking about the linear coefficient of thermal expansion. If you see alpha V, that's the volumetric coefficient of linear expansion, all right? And remember there was a relationship we were talking about the last time about volumetric strain with linear strain, right, for a cube? Remember how we said, okay, the volumetric, the deviatoric, or the E, right, the volumetric strain is equal to 3 times the lateral, the edge strain, okay, on a cube, all right, in any one dimension. It's kind of similar here. The coefficient of volumetric expansion is equal to 3 times the coefficient of linear expansion, okay? And then there's some values here if you want, okay? So, what you get a chance to do is do some problems like you'll see here, where maybe we have an unconstrained beam and then we have to apply a load to go back, right? And figure out, okay, what is the amount of force required to do that? Well, the amount of force, the material properties have not changed. What has changed is the length. So now what we have to do is we have to figure out, okay, what is the displacement that we need to apply to get it to go back to its original length? Okay. And then a somewhat complicated problem is what happens if you have 2 materials between fixed walls, okay, and those materials have different elastic modulus, different length. In this case, they have the same area, but they could have different area, right? What happens if you heat up everything uniformly? And you can ask yourself the question, okay, what's the force that builds up, for example? And maybe another question is, how far to the right or left does this middle between them go, okay, under the circumstances? And there are 2 ways to do this. One is using geometric compatibility, and the other is to use superposition, all right? So, and I include instructions on how to do both of those. There was a question. Yes? Okay, so here is the middle, right? Okay? It's kind of like a tug of war. All right? For example, let's do some thought experiments. Let's say that the lengths and the areas are the same. The temperature increase is the same. But that the E1, the elastic modulus on this one, is much larger than the elastic modulus on this one. In that case, which direction do you expect this to go? To the right? Because that high elastic modulus essentially is bullying the one on the right. It just says, I don't care. You got nothing on me. All right. So like this is going to be maybe like your metal, and this is going to be like a I don't know, another material. Assuming alpha 1 and alpha 2 are the same. Now it gets a little bit interesting, right? Because sometimes for the plastics, even though they have a much lower elastic modulus, their thermal coefficient of expansion is much higher than it is for the metals. Okay? So you had to take into account these factors. Good. Does that help answer the question? Right? What if you have exactly the same materials, but L1 is much larger than L2? And I heat it up. Which direction will it go? That's a hard problem. All right? That's a hard problem. At least I think it is. Because L1 now, if I have a longer L1, that means its stiffness is less, okay, than the one on the right. Okay? But there's more of it. So I have to think about that one a little bit better. If I come over here to the answer, the strain, all right, let's see here. If all these things are the same, where's the... I should know this, but I have to think about this a little bit. That's what happens when you ask a tough question. Yeah, I had to think about that. We'll get back to you on that. All right, I don't want to say the wrong thing. It's either left or right. Okay. All right, so go for it. Let's do the attendance and let's. All right. Oh,
We were working on it outside.
yeah, I'm sure.
No, we can.
You
I'm
were?
actually very frustrated. I'm
You're
very
actually-
frustrated because I can't figure it out. I've attempted it like 6 times now and I can't get it. I can't get
Okay.
the.
I can show you too if you.
Yes.
Last class,
Yeah.
forgot to do it one time tonight, unless you by chance.
Yeah. Over campus. Over campus.
Question. When you run the analysis, right, and then you switch it to E22, right? That's
When I
right.
switch it to just watch the what? When you switch it to what?
You switch it to E22, right? Is that what you switch it to? When
Yes.
okay. What magnitude is that supposed to be at? So
So
like what 10 to the what powers? I've been getting 5s and sometimes 7s when if I forget to scale it.
okay.
So-
So the Poisson ratio. So let's just say that. So first of all, it should be equal, right? Because it's going to be if I'm stretching this direction, it's contracting this direction. And the typical ratio is 0.3, right? So that let's say that the Poisson ratio is equal to negative strain in the latitudinal direction over the longitudinal. So whatever you had for your longitudinal times 0.3 is what it should be. Okay. Okay. All right. Okay. Yep. All right.
And when you are doing it in CAD,
Yeah.
and you're converting it to centimeters, or are you making it millimeters?
So I went ahead and I put it in the CAD as I wanted it. So I put 1 centimeter, 1 centimeter. I can type in 11 centimeters if I want, whatever I want.
Yeah.
But it's going to automatically know. Like it even changed my 1 centimeter and typed in 10 millimeters. Right. So it's
No, because I'm wondering because I want to know like what to scale it to.
Okay, so typically if you use FreeCAD, right, you're going to need to, and you use the default settings that I use, then you're going to scale by 1 over 1,000, right, 0.001, okay? If you use another package, then look at this, okay, then use the scale bar, right, and take a look at the scale bar to get an idea of, okay, it's off by a factor of 10, it's off by a factor of 100, and then you've got to multiply by the appropriate factor. Okay?
Thank you.
All right, yes. Okay. Yeah, you won't run on it. So you gotta run it on the computer. EIT or NIST. Okay? Yes. Go ahead. Yes.
I use these two
Yeah. 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 Okay, so once you've got the deltas, right? The question is asking, what is the question asking? It's asking for strain? Yeah. Okay, so then you can pick, right? Well, so you know that they're going to be the inverse of each other, right? So like delta BA is going to be equal to minus delta BC. Okay, so just pick one of those, take the delta BA, and that's what you're going for, because that's what.
So I'm just gonna
You can pick either one. Yeah. That's what it should. Yeah. All right. No, but it's in. But we want to know the displacement. Yeah. And so you got to convert it to microns. Yeah. Okay. Yes.
This is for session 7 of the last one.
Okay.
So this is the formula from it's like the displacement of the time of the lid, and then this is what I'm putting on top of here.
Okay. Well, I don't know either, to be honest. So first off, okay.
This was me working out to make sure it was right.
Yeah. So if we look at it,
Exactly.
yeah. Yeah. Okay. So if we okay. So I agree, and we're asking. What am I asking?
It's the actual
Which one is it? 5 or 6? Okay. So you don't need area. Where's your 1,000? So the track of your units 1,000 kilograms per meters cubed, and your omega squared is whatever. What did you put it? It was 102 radians per second. Okay, squared. Okay, L cubed. What did you have? Okay, cubed. All right, and then 3 times 200 times 10 to the 9. Yeah, I would expect that to work. And then you've got a
times 10 to the 6, so that should give me meters for microns.
yeah, that should be a
I mean, I'll try it, but
yeah. I don't know.
I've done it like 6 times. And
Yeah. Okay. So yeah, you can try it again. Let me talk. What's your question?
I was trying to like follow along and like do everything,
good.
and when I like ran it, it kind of just like didn't work.
Ah, yeah. Okay.
So I don't like I have like I did like the material, I did the section. I did.
You recorded? This is the video you're on.
Oh no, I'm using.
Oh, you're using mouse.
Oh,
Like,
yeah,
wow, that's
yeah.
wow. How's it
No,
moving?
yeah,
Okay.
no. So yeah, I have like the section. Is that where the rigid body is supposed to be?
No, the rigid body should be on
the
this
force?
side, where the force is.
Oh.
Yes, and then there needs to be a fixed. So where did you do the fixed? Okay, but now we need to select a different surface. So just delete it. So just delete it. That's fine. That's good. Now you need to select this surface. That's good. Now hit OK. Okay. Now, is the constraint there? Can you go over to boundary conditions? Yeah, it's missing the boundary condition. So
Is that?
this needs to be fixed on the side.
Oh, I see.
So now, if you rotate it a little bit first, then you click on it, and then hit OK. And then you run it.
Is that? How do you run? Oh,
Analysis.
ready? Or run? Oh.
That is rather odd. Let's go back to your other thing. Let's take a look. Go to FE model.
I'm at it.
Okay, so let's take a look here. Alright, so
is it okay if I touch
Yeah.
this?
So this reference point, I'm just going to delete this reference point.
Yeah.
Need it. In fact, this This is on the surface, I think, so I think that's okay. Selection, fixed, surface. We got that. No, we don't want reference, we want the surface. So just make sure, can you rotate it and make sure you. Oh, that looks good. Yeah, so just click on it though again. Yeah, that's, I don't think that's the issue. So, okay. Okay, so that looks good. Concentrated force. Oh, you have 0 newtons.
Oh, I thought.
Oh, I see. No,
How do
we
you-
want a 0. That's just magnitude, but it has no direction.
Oh.
Okay, so this is going to be in the one direction. Or I don't know what you have. Whatever.
1911. Oh, I see.
Now let's try it.
Oh, and you were talking about something about the concentrated force where like it acts on every point.
Right.
Is there,
But we use a rigid body, so we should be okay.
oh.
There you go.
Oh, okay. Thank you.
That was all.
Excuse me.
Sorry about that.
Is this mine or yours? Mine. Yes. Hi, Ryan.
Sorry to interrupt. If you guys are done, do you mind if I turn the projector off? If
Um,
you're still using it, no worries.
Yeah, I think you can. I don't know. We got 10 minutes left.
Okay.
Might-
I can just show you how to do it.
Yeah, sure, that'd be
Just-
great.
Okay. Yeah. Sorry to interrupt.
No problem.
There was the remote somewhere. Oh, that one there.
If I just click on this, can I do it?
That's my.
Okay. Yeah,
That'll
do
be
it.
just this, I think.
Okay.
I think that might just be here though, for the.
Okay. So then this remote will be.
Yeah, if you hit standby, there, and then it'll give you a sign.
Okay.
And it's
Sounds
gonna
good.
do-
All right. Great.
Thank
Thank you,
appreciate
Ryan.
that.
Wait,
Okay.
really quickly, is this supposed to be like that? Like, I thought it was supposed to be. Like, it seems weird. I thought it was supposed to be
It
like
does seem
kind of
strange.
parallel to like, the surface.
Yeah. So the. It says it's in the one direction. X is in this direction. Oh, but it is.
Is the model not like fixed in the correct position?
It should be fixed on this side. I think it's a concentrated force on selection. Oh, this goes on a point.
Oh.
Let's try that. Okay, and then I need to take a look at what other people have. Okay. All right. I have no idea because it changes for every single person, right?
Yeah, but like around like 12, somewhere in that like
Yeah.
2 digits. I literally didn't even actually process every single time.
I don't know what to say. I'm sorry.
It's all good.
All right. Good. All right. Hi, Jesse. What's up?
Yeah, so I try to do the thing, like I have a Mac, so I have like the whole like Windows thing. I
Yeah.
here. The
Yeah.
problem is when I try to select it, it just crashes like every time without fail.
Yeah. I don't
So,
know what to say.
Like I don't know what I should. Is there any?
Just go to the computer lab and do it.
I guess I'll do that.
Yeah. I'm sorry. Yeah.
Do you know how much more of this is gonna be in the class?
Like 1 or 2 more.
So it's not
Yeah.
gonna be.
It's
that
not
big
gonna
of a
be.
deal.
It's not gonna be something.
Yeah, I guess we'll just have to head to the lab. So it's,
Yeah.
that's fine.
I'm sorry, Jesse.
Yeah, it's fine.
Yeah.
Let me know if they install FreeCAD or if they install. I haven't because they asked me what I wanted to install on the computers, and I said these software packages, but I don't know if they install them.
I don't think it's there. I just downloaded it off the internet.
Yeah. I mean, that's once you load the. I have been in the computer lab in the past, and yeah, I've checked. You just download. You run the virtual Windows there, and it runs.
Yeah. All right.
Okay.
Okay, so
Yes.
for last times 3,
Yeah.
so it's asking for the force, so you don't have to take an integral. Like, 3 is asking for just the force at that point.
Yeah, you have to integrate the distributed force, right?
Okay, so when I was integrating it,
Yeah.
I was getting the wrong answer, but then when I wasn't integrating it, I was getting the right answer.
I don't know what to say. It's
And I did it like 3 or 4 times each way, and each time that I integrated it, I got the wrong answer, and each time I did not integrate it, I got the right answer.
I don't know. Was the distributed force correct? So this is the distributed force, right?
Yeah, exactly.
Okay. So then I've got to integrate it, right, to figure out what P is, the internal force.
No, it was asking what the distributed force was at that point, so that
This is the answer. That's this answer.
Okay.
Yeah. You just plug it in there. Yeah.
So okay, that's the first thing.
That's the distributed force, right?
Then for 4, I did all of the integrals, and this is what I got,
Okay.
but it's wrong.
Yeah.
But then I accidentally put it in this way, and it's right.
I don't know what to say.
So when you're doing the integral for 4, which is you need to find the internal force at a certain point, like L over 2. So you're gonna take it. The integral.
Okay, that's an interesting way to write it because it's not a cantilever beam, right? So just so you right, it's actually going this direction,
Okay.
right?
I was just
Along-
thinking because
yeah,
that's
yeah,
how it
yeah.
shows it, but it's
No, it's going along the beam.
Okay, so then halfway, then the force is going out, the distributed force is going this way.
Yeah.
But are you gonna take it from 0 to L over 2, the integrals?
So
Or is
you're
it-
gonna do so. I mean, what I would do is I do an indefinite integral 1st, right? Or actually no. So if you need the entire length, right?
Yeah.
You do 0 to L.
Yeah, so the 0 to L will be the force on the end, the what's it called, resultant.
Well, no. So we have an expression for the internal force, right?
Yeah.
So P is changing as a function of x,
Mm-hmm.
right? The internal force is changing as a function of x. You have to integrate that.
Wait.
So that's why you have to integrate. You have to
internal
integrate.
force is always gonna be that, and the
That's right.
external. Oh my god.
You have to. Well, the distributed force changes, right, as a function of x, and so does the internal force. Okay, that changes as a function of x, and so that's why you have to use the integral form. Otherwise, it's just PL over EA, right? Because E is constant, A is constant, right? L is a
And then
length.
to find whatever internal. Oh, that's what I was doing. So what I was doing is just because that messed me up that I put it up and down because I was doing the distributed force minus it looks like this up, but that force equals the internal force. But it's in reality it's just the internal force of.
Well, it depends on which side you slice.
Yeah.
Right? If you slice such that, and that's what I was trying to do in this was help people out. If you slice from this side right here, okay, and you expose the left side, right, then you don't have to worry about a reaction force at the middle, right, on the system. All you have is distributed force on this on the right.
Okay, so then you would just literally just use P of x, and then.
Yeah, that's right. And the integral of the distributed force
That's
over
why,
that length will equal to the P of x.
That's why this one was working because this is just literally just plugging it into the integral.
And I when people show me their stuff that fast, there's no way my brain can compute everything and how that's different than this.
Yeah.
Okay? I hope that helps. What's your name?
Anthony.
Okay, thanks.
How's it going?
Yes.
I run track and field.
Okay, yeah,
So
yeah.
these are like my travel letters.
Okay,
And then the ones that I have highlighted would be the ones that I missed class.
okay.
And would you be able to just sign it? Just to, like.
Okay,
note
can you
that
send
I-
me an email? There's no way I'm gonna remember this.
Yeah, but I just need it for like the record to give back
Okay,
to my
that's
advisor.
fine. That's fine. I just can't remember. So
Yeah,
you're gonna
I'll
have
send
to-
you an email.
You have to send me. Yeah, send me
I
a
missed.
message the day that you're away. Oh, okay. Well, that's good that we changed our exam not to be that day.
Yeah. But I missed dynamics.
Oh, I'm sorry about that. Okay. Yeah, and exam 2 is on. When is exam 2? I have to check. But are we good for exam 2? I think so. I think exam 2 is the Tuesday before Thanksgiving, and these are Thursdays, so it's not that. What do you do for track and field?
Like this.
That was a horrible distance. I did it. It was fun though. I did it for the bus rides and the fun and the camaraderie and the exercise too. What's today's date?
28.
Okay. All right. Good. Good luck.
Send it.
What do I have? Oh, there's.
The one's for you, and the other one's.
Oh, okay.
You can do whatever you want with it. But... You can keep those two, and then I'll take this one.
All right, great. Okay.
Sorry. Yeah.
Students copy.
My bad.
All
Thank
right,
you.
great.
Appreciate it.
All right, we can handle it. Okay, what's up?
I just have a question. Right? So the question to me is asking for the height of the bar on microstrip.
Yes.
So would that be E22 or
Right. So E22, right, which is going to give you a negative.
Yeah.
Okay. Should give you a negative.
Yeah. Right.
But so go ahead and click on query somewhere. So like right click on something. No, over here. Just click. Now you've got the query up. Don't close it. Keep it open. Right click. Query. Then click left click. There you go. All right. So see that value is minus 2.268.
Yeah.
Instead of minus 5. So that's epsilon y essentially, right? In the height direction. So how do I figure out what the change in height is now?
Well, I have to grab the change in height would be the original length times the change in
Times epsilon times the strain, right?
Right.
And that's it.
Well, that's it. But the question's only asking for microstrain, so it would just be that value then.
That value times 10 to the 6.
10 to the 6. Yeah.
Yeah.
Okay. Thank you.
No. It's asking for microstrain or micrometers.
That's actually microstrain.
Okay, then it's just that
Yeah.
times 10 to the 6. Okay.
Thank you.
I can't even keep things straight. All right.
I want to ask, so for this question,
Yes.
like essential line, like what would be the general approach to
Okay, so there are two approaches, right, which are outlined in the video and in the notes, right? One approach is say, okay, I'm going to think about calculating out what the displacement between these 2 points is and what the displacement is between these 2 points, and I'm going to add them together. All right, and they have to equal 0. Okay, and that's geometric compatibility. All right. That's one approach, and that's actually, it turns out to be the less mathematically intense approach. And that has to do, and what you can think of is you have a thermal strain, okay, and then you have a force-based strain, okay, and they also counteract each other, and they're gonna work against each other, and you can see that in notes. The other approach is to use superposition, okay? And that was kind of my first, that seems maybe a little bit more intuitive to me, but it involves more math. It ends up being more complex mathematically, right? So what you end up doing is you say, okay, I release this right end, and I apply the temperature to the whole thing. And since it's unrestrained, I can figure out what the overall strain is, right? I can figure out what the strain in the first one is, the second one, I can figure out what the displacements are, right? And then I've got to apply a force that gets me a displacement that counteracts it and gets me back to 0.
For that, do we use PLE to get?
So it's more complicated than that because now these things are essentially 2 springs in series with each other. Okay? Right? Because it's unconstrained, right? They open up, and then I've got a force that's going to be the same in both of them, okay? And that's what I got to apply to get to 0. And I go through this in the video in detail, okay?
So after you find the individual force, both you just pick one of the bars and apply displacement.
That's right. So if I know the force, exactly right. If I know the force in the bars in either one of them, and I know what the change in temperature is, right? So now I can figure out what the strain is from the force, and I can figure out what the strain is from the temperature, right? And then yes, that will give me a net strain that I can multiply by the, or it gives me, I can think of displacements. Probably better to think of displacements, right? Does that make sense? So I know what the displacement is due to the strain, or displacement due to the temperature. I know the displacement due to the force, and I can add them to each other.
It's like defined based on the reference system, right? Like it's because we
displacement of the force is compressive versus the
Yeah.
displacement due to the temperature.
Yes, that's right. That's
So
actually
just
right.
like look at both sides left and right.
That's right. So you know that the thermal displacement is going to be expansive, and you know that the force is going to be compressive. That's right. Or you know that
The force is
the
because of the
displacement.
thermal expansion. It's because
Yes.
of its hitting the
That's
wall.
right. That's right. That's right. It's not a trivial problem. It's not a trivial problem. So it takes some time to go through that. Okay. And your names again were?
Oh, okay.
I keep forgetting your name. You keep asking good questions. And your name is?
Vermont.
Vermont. Okay. Great. Your name?
I'm Hannah.
Okay. Great. What's up?
I think I actually have the same problem.
Okay.
Because of this memory.
Mm-hmm.
So how do you combine, like, do you combine the two after you solve these problems and then you get like the codes?
So this will tell you what the stream is in the first one and what the stream is in the second. Okay. But to figure out what the displacements are, right, you need to multiply by the elements of those different, if you know those different elements.
So then, because they're like two strain values, you're gonna get two displacement values. How would you combine them?
So yeah, so one will end up being positive and one will end up being negative. And when you add them together, when I say one, like one displacement will be positive and one displacement will be negative. And when you add them together, they better equal zero.
Oh wait, so then
They're going to, because those are going to equal, like, so you're going to have some motion to the right or some motion to the left, but the overall displacement of this one plus this one has to equal zero.
wait, so then the answer is zero?
No, the answer is not zero because we're asking what is the displacement at the mid-mark.
So then how would I get?
So you have a choice. You can say, I'm going to look at the left bar and calculate out what that displacement is. And that's going to give me how much it goes to the right.
Oh, so I just need it for like one.
Yeah, or I could look at the displacement on the right bar.
Oh, so
And
that
that
means
because-
just either one.
That's right.
Oh, okay. And then also, I just wanted to double check my formula for modulus of toughness.
Okay.
Is that right?
Okay.
Like this ending part?
Yeah, so the modulus of resilience is UR, right?
Yeah.
Okay. It's okay. So first off, you're assuming that this is a linear elastic, perfectly plastic material.
Wait, so when you say that, you mean like this?
It goes up and it goes horizontal,
Yeah, so, okay.
right? No, not that. Right, exactly. If it's that, then you have to remember you used to add the trapezoids or add them up. But I'm a little confused on what you're considering this epsilon y percent. I think as long as you're defining that as what the yield is, like after you've gone up and over, like as long as you're defining it as the horizontal length, then you're fine.
So on the exam, you would just be either to like do the area or like do the
So if you're given a graph, it's easier just to do the area, but it's not bad to write this down because you're really only going to have two choices, right? It's either, well, you're probably only going to have two choices. It's either going to be a linear elastic perfectly plastic model or a linear elastic linearly plastic strain hardening model, right? I could give you something where you have to like actually guesstimate, right? Like I'd be like, yeah, you know, and then like do like, so you should be able to do it for those two and know how to figure out the area.
If I define ER as like this, without area.
Yeah, this is good. I like that.
Okay.
I like that definition. Yeah, and you have it. You said it percent, so it's kind of weird. So you multiply by 100. I mean,
Well, I
yeah.
just wanted to make sure like I knew to make it like the decimal.
Yes, right.
Okay.
Yeah, good. Good, Hannah. Yeah, good.
Thank you.
All right. What's up? And I can't remember your name either. Max. Yeah. Okay.
So I have a question.
Yes.
So this one uses Poisson's ratio,
Yes.
but this one doesn't for calculating.
Ha ha.
The formula they use about Poisson's ratio is
Yes.
right.
Yeah. So look,
the finite element analysis is using Poisson's ratio because you had to put it in as one of the material parameters.
Yeah, but when I calculate it, it's like, it's right when I don't use it. If when I put it into like this. Like you
So
can't-
what's the first problem? This is well, because you don't. This is the actual stream in the length.
Oh.
So there's no right. Remember the formula that epsilon x is equal to 1 over e times sigma x minus nu times quantity sigma y plus sigma z. There's no sigma y. There's no sigma z. So that quantity is 0.
okay.
So it is just sigma equals e epsilon essentially, or epsilon equals sigma over epsilon, or
Okay.
sigma over e.
I was trying to figure out what was wrong. So
Yeah. But for the vertical, yeah, you need the Poisson ratio.
Okay, got it.
Okay, and the finite element, I actually didn't do that in class, but you've got it, Max. You've got it.
Okay.
All right.
Thank you.
Very good. Very good.